precession of the lunar core. And this is going to have some exciting implications for lunar magnetism. So hold in there through the boring parts. Just kidding, not going to be boring. So before we start, I want to do a quick review of the Cassini state of the moon. So the moon is in Cassini state 2, which means that these three vectors shown up here are coplanar and precess together with an 18-year period. And so you can see here that this is the normal to the orbit, this is the normal to the ecliptic, and this is the spin axis of the moon. So they're offset by this constant amount from each other and precess together. All right, so in order to figure out what obliquity the Cassini state is at, you write down this equation right here, which is basically balancing the precession due to gravitational torques from the sun and the equatorial bulge of the Earth that are torquing the orbit, and the precession of the spin axis due to gravity from the Earth. So you have this equation where capital I is the obliquity, and the other things are, moment of inertia and orbital frequency, things like that. And you solve for the obliquity I, and these solutions are called Cassini states. And there's 4 of them. And as the moon evolves outward in its orbit, so here we're showing the lunar semi-major axis as we start close to the Earth after formation. Here's 10 Earth radii, and here's 60 where we are today. So you can see from this diagram that state 1, where we believe the moon formed, is going to evolve outwards until about 34 Earth radii, where it merges with state 4 and becomes unstable. At that point, the moon's spin axis is forced to jump to the only other Cassini state available to it, which is Cassini state 2. So at this point, we're tipping the moon from 26 degrees in one direction, like this, all the way over to 49 degrees in the other direction. And in fact, the moon actually overshoots and gets up to about 77 degrees before sort of ringing back down to equilibrium. And because the moon wants to always rotate about its maximum moment of inertia, this means that the entire moon is going to reorient itself during this transition from state 1 to state 2. That's called the Cassini transition. Okay, so keep that in mind. Here's a diagram showing where at the time of the Cassini transition we would be in state 1 and state 4 merging, becoming unstable, and we tip all the way over to state 2. All right, so that will make the punchline much better when I get there. All right, so the motivation for this study was for trying to figure out why the lunar rocks are magnetized. So as you probably heard from Ian an hour and a half ago or so, there are 2 plausible mechanisms for how rocks on the moon could acquire a magnetic field. Since the moon doesn't have a global dipole, it's either impact-generated magnetic fields, where the plasma that's generated by an impact will magnetize the rocks, or a core dynamo. Now, there isn't enough energy from convection to power a core dynamo like we have on the Earth, and so instead we have to turn to some other kind of power source. Dwyer and Stevenson in 2005, in an AGU abstract, showed that mechanical stirring due to precession is the only way that we can get enough power to get a long-lasting dynamo happening on the moon. And this has been updated in a LPSC, I think, abstract this year by Dwyer, Nimmo, and Stevenson. And so this stirring mechanism requires that the core and the mantle are not locked together, so that there's some mutual motion between them that will allow the fluid in the core to be stirred up and give us our dynamo. All right, so here's the diagram I showed before of the moon's mantle. Now we're going to add on the core. So today the core spin axis is aligned with the ecliptic. It's not locked to the spin axis of the moon. So there is this mutual motion between the two, and if only the power was enough, we could have stirring today. We could have a dynamo today. But the stirring's not enough right now. So why am I concerned with this? And the problem is that in the past, inertial coupling could have been happening, which would couple the spin axis of the core to the spin axis of the mantle. And if this happens, no more dynamo is possible, which would preclude having a long-lived magnetic dynamo to magnetize the rocks that we find on the surface. So inertial coupling is a mechanism that is operating on the Earth today, and the basic idea is that the core-mantle boundary is elliptical. So you have motion moving inside an ellipse, and because of that, there's different pressures at different points in the ellipse. And these pressures act to torque the fluid inside the cavity to align with the spin axis, or to align with the shape of the cavity. And so it's just like if you had a 2-liter soda bottle full of water and you start rotating it, you would expect the water or whatever inside to align with the shape of the bottle. And so if the cavity, if the core mantle boundary is elliptical enough, it's going to be able to torque the core spin axis to align with the mantle, and no more dynamo for us. All right, so how can we figure out whether this happened in the past? The argument for why it could have happened is because the moon was much closer to the Earth, so the core mantle boundary would be much more elliptical, because the moon would also be spinning more rapidly since it's in synchronous spin-orbit resonance. And so we need to compute what the precession timescale would be for the core and for the mantle and compare the two. So the natural precession frequency of the core is equal to the precession frequency of the orbit, so this is 18 years, times the flattening of the core mantle boundary, where the flattening is just a measure of ellipticity. And if the mantle precession frequency is greater than the core precession frequency, then the core will not follow the mantle. All right, so this is saying that if the mantle is moving very rapidly outside a naturally slow-moving core, the core is not going to be able to follow along. But if the opposite is true and the mantle is naturally a slower mover than the core, then the core will be able to follow the mantle. Locking will occur, no dynamo. So in order to compute this, all we need to do is to know the flattening or the ellipticity of the core mantle boundary at every point since its formation. So we calculate that. We do this by writing down the potential for a given mass element inside the moon. There's a rotational component, a tidal component, and then a U sub m, which describes the potential due to all of the other mass elements in the moon. And this potential is going to depend on the shape of the moon, the shape of the moon's mantle, to be more specific. And so we treat two different cases. We treat the case where the moon is in hydrostatic, the moon's mantle is in hydrostatic equilibrium, and then we treat the case where the moon has the fossil shape that it has today, which is not in hydrostatic equilibrium with our current orbit. So when the moon originated, it would be all warm and melty and would naturally have a hydrostatic shape. At some point, the moon had to freeze in the shape that it had today. Since we don't know at what point that happened, we're just going to follow both cases along until the end and see how they differ. All right, so assuming that the core mantle boundary is hydrostatic, though, we solve for what the shape would be, both numerically and analytically, and check that they match. And here's the results that we get. So this is showing the semi-major axis again, starting from very close to the Earth and moving out to 60 Earth radii where we are today. And then this is showing precession period from 0 to 150 years. A shows the precession frequency of the orbit and the mantle. They're the same thing. And B and C show two different curves. B is the curve for the precession frequency of the core. Sorry, I should be saying precession period since this is plotting period. The precession period of the core for the case of a hydrostatic mantle. And C is plotting the precession period of the core for the case of the moon having the shape that it does today, the fossil bulge case. And so you can see that curves B and C cross over curve A right here, which means that before this point, before 26 to 29 Earth radii, depending on whether the moon is frozen in its shape at that point or not, the core spin axis and mantle spin axis are locked together. After 26 or 29 Earth radii, the core and mantle spin axis are unlocked, and a dynamo is possible. So in order to so you should note on this that there's this gap in curve C. Curve C is the one with the fossil bulge, and that's due to the Cassini transition, as I talked about earlier. So this means that the Cassini transition is happening after the core and mantle have transitioned from being locked to being unlocked. So this means that when the moon undergoes this dramatic rotation from negative 26 degrees over here all the way over to 46 degrees, the core is not following along. It's unlocked from the mantle. So you have this fluid inside a cavity that's rotating, and then all of a sudden the cavity is going to completely rotate. So this is going to be probably a big stirring event for the lunar core, and is possibly a good source for jump-starting a dynamo on the moon. So in order to evaluate this hypothesis, we need to be able to compare it to magnetic data. And so this is a plot from Wozorek 2006 that's updating data taken from Szyzowski and Fuller in 1987, and it's showing paleofield intensities for all the lunar samples that had been measured at that point as a function of time, where this is oldest and then this is the very youngest. And so they say that this points to a magnetic era between, I think it was 3.7 to 3.95 or something like that, billion years. There's been more recent data, for example, from a paper by Ian Garrick-Bethel, 2009, showing a lunar sample that's 4.2 to 4.3 gigayears old. So that's, before the supposed magnetic era, but definitely showing signs of magnetism. So in order to figure out whether the Cassini transition was responsible for jump-starting the lunar dynamo, we need to have many more data points in the old region of that plot to see if there was a time that lunar magnetism turned on or not. And we also need to be able to evaluate when the Cassini transition happened, not just in terms of semi-major axis of the moon, but actually in terms of time, which is a separate problem I can tell you about in the question session if needed. So in conclusion, the core does not precess with the mantle today, but when the moon was close to the Earth, it did. And the core unlocked from the mantle at between 26 and 29 Earth radii. Before that point, it would be impossible to have a lunar dynamo. After that point, we encounter the Cassini transition at 34 Earth radii, which is possibly a very good source of jump-starting a lunar dynamo. Okay, thank you.
Okay. This is a really nice piece of work. I really like all the implications here. So once you jumpstart the dynamo, how long does it continue? Do you have a feeling for that?
That's the question everyone asks. And that's going to require some actual modeling of the dynamo. So in order to do this, we would have to figure out, due to the reorientation of the core mantle boundary, what sort of fluid velocities are we going to get? And we would have to figure out how long that takes to damp down, which requires knowledge of, the viscosity of the core fluid. And so it's not a job for me, but I have been encouraging everyone I know who works on dynamos to work on it.
Okay, and I have another question, but I'll see if anybody else has to go first. Oh, okay. If not, I'll catch you at beers.
Okay.
Hi, I'm Matt Sigler, UCLA. So Bruce Bills and I have been working on the Cassini state problem a little bit. And we found when you use a more hydrostatic moon, you can actually get that Cassini state transition even earlier than 34 Earth radii. So, we got, by using a semi-hydrostatic body around 30 Earth radii, would that affect what you're seeing here? How?
Well, so the transition to an unlocked core happens at 26 Earth radii if you're talking about a hydrostatic body. So then the Cassini transition would still be after the
Okay, so as long as
unlocking.
it's after, the result will look
Yeah.
pretty similar? Okay.
Yes.
And then, if I can ask another question, is there a big heat flux output associated with this as well, or just a magnetic anomaly? I mean, would you expect volcanism to pick up or anything like that?
I don't have a good feel for that. I have no reason to expect a very dramatic heat flux.
Thanks.
Okay, thank you. We better move on.
All right, so I'm introducing